Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this video, we're going to cover the big S in the sky, stoichiometry. This is one of the most fundamental chapters or fundamental topics that you're going to cover in general chemistry. And I found myself when I was working in the laboratory, the calculations that we cover in these upcoming slides are some that I found myself doing the most often. So I'm super excited to kick off this chapter. So let's get started. So when we look at counting and predicting quantities that are going to be needed for chemical reactions, a lot of the information that's found in the chemical equation will help us out. And so we just learned in a previous video that as we are writing these chemical reactions, that we must be observing the law of conservation of mass. And we do this by actually ensuring that we've balanced the equation, ensuring that the atoms on my product side equal the atoms that are on my reactant side. Remember, when we're balancing, we're only placing changes to the equation in that coefficient position, the position that precedes the element or compound that you're dealing with. And so what we're going to be studying in this chapter is actually looking at the numerical relationship that exists between each of these quantities found in a chemical equation, and this process is known as stoichiometry. So reaction stoichiometry is really essential because what it's going to help us understand is a new relationship that we can rely on to help us predict the relative amounts of substance that are required for this reaction to go and how much of a product could be produced. And so the coefficients, again, those have to be balanced in a chemical equation in order to get ready for this stoichiometry piece. And so after we balance an equation, we could read those numbers that we put in that coefficient position in a molecule or atom idea. So in this case here, where we have C8H18 reacting with oxygen to produce carbon dioxide and water, well, we could read this as 2 molecules of C8H18 reacts with 25 molecules of O2 to form 16 molecules of CO2 and 18 molecules of H2O. But we could also think about this, just like we did back in chapter 2, as rather than a molecule to molecule ratio, we think of this as a mole to mole ratio. Again, we're arbitrarily counting things. And so we can apply this idea of a mole to these coefficients. So rather than thinking this as 2 molecules of C8H18, we're going to think of it as 2 moles of C8H18 compared to 25 moles of O2 to 16 to 18 respectively. The reason it's important to think about it in moles, well, remember through Mole Island, we learned that we can connect a lot of different units to one another if we can relate them back to the mole. And so if we think about these coefficients as moles, that's just one more way we can connect the dots between the different items that are found in these chemical reactions. And so this ratio that we're going to use is going to become a conversion factor that's going to allow us to go from talking about one thing in an equation to another. One of the best things we can do with this information is to actually predict the amount of either product that may be produced or reactant that is needed to produce a certain amount just by simply observing those ratios that exist. And so if we look at the ratio, for instance, of like C8H18 compared to CO2, well, the ratio is a 2 to 16 ratio. And so if I was asked how much CO2 can be made from 22.0 moles of C8H18 in this combustion, well, we can use that to predict how much will be made. Well, how, you may ask? By simply taking our 22.0 moles and setting that as our given, and then using that conversion factor, this 2 moles to 16, as a means to get to what I want to get, which in this case is moles of CO2. And so I can now plug that in and say, well, I would put my moles of C8H18 on the top and moles of CO2, moles of C8H18 on the bottom, then moles of CO2 on the top, and fill that in accordingly with 16 on the top, 2 on the bottom. Now, when we plug that into our calculators, what we end up seeing is 22 times 16 divided by 2, and that gives us a total of 176 moles. And so through this, we were able to convert from one substance to another by exploiting that relationship that exists between the coefficients. So put a star by this slide. I absolutely love this slide because this is really going to be the reference that you are going to want to use as you're doing a lot of these stoichiometry problems. as we go through the rest of chapter 4 and into chapter 5, we're going to see that we're going to keep building out this diagram, which I call mole bridge, and be adding to it. And what it really serves as you is another visual tool that you can use during your studying. So let's just take one step back and remind ourselves about Mole Island. Okay, so Mole Island, remember we had the mole in the middle, and then over here we had our grams, and over here we started filling this in with atoms, molecules, formula units, things of that nature. And so that's still going to be very prevalent in this part. We know to go from grams to moles, I'm going to use the molar mass set to 1 mole. And we get that information from adding up the amounts from the periodic table. And we can go from atoms to moles using Avogadro's number. Okay, set to 1 mole. Well, now, what I want you to remember, what I used to say in those previous videos, is that no matter what kind of problem you're dealing with, especially these stoichiometry problems, your first objective is going to be to get to moles, however you can. So if your given is in grams, you're going to use the molar mass. If it's in atoms, molecules, formula units, you're going to use Avogadro's number. Whatever it takes to get to moles first. So in mole bridge, you may be starting in a position that's found here. And that starting position really just represents if you're in anything but moles. So if you're in grams, atoms, formula units, whatever, we're going to expand that list even further. Our first objective is to get to moles. At this moment, the only way you guys know how to get to moles is through some relationships that you see in Mole Island. So either you're going to use the molar mass or Avogadro's number. Then after you've gotten to moles, we're in moles of the given, our next step is to walk across the bridge, to get to the other side, get to talking about the compound or element that we care about, the thing we're trying to solve for. And so to get to the other side, to cross the bridge, that's where you're going to apply the mole-to-mole ratio or the coefficient conversion factor that exists. And then if you want to get to anything, solve for anything except for moles, then again, you can use Mole Island, and we're going to learn some other things we're going to add to this in later sections. So again, basic rule of thumb, if you remember nothing else, first step is get to moles however you can. Then use the mole-to-mole ratio, the coefficients, and then get to what you're trying to solve for using either things like Mole Island or some other concepts we're going to learn later. Okay, so let's try this in a problem. So it says, how many moles of water are made in the combustion of 0.1 moles of glucose? And so glucose is our carbon compound right here. And I typically will actually go ahead and write the values right under it, just so I can make sure I'm focusing on the parts of the equation that I care about. So I know I have 0.1 moles of glucose, and I want to know how many moles of water are made. And so if I were to draw my bridge, I know it's going to look something like this. And I physically draw this when I'm teaching this class. I physically draw it so that I can focus. These are the things I need to relate to one another. And so if we start with the first one, we have 0.10 moles, and we think about our mole bridge concept. Well, in this case, we're already in moles. And so we know that we don't need to do a step to get to moles because we're already there. So then the next step, so we're here, I want to walk across my bridge. And how I do that is by applying the coefficient, the mole-to-mole ratio. And so I would put my moles of C6H12 on the top. So on the bottom, I don't know why I keep saying that, on the bottom. And then on the top, we're going to put moles of H2O. And we're going to fill this in based on the coefficients we see. So make sure anytime you're doing these stoichiometry problems, you always check to see if the equation is balanced. If it's not balanced, then that's your first step. You really need to balance it before you even attempt to read or look at the problem, okay? At least I recommend it. And so now if we fill this in, we would put 6 moles of H2 on the top, 1 mole of glucose on the bottom. And we see we're at our desired units, so we'd stop there, a one-step problem. When you plug this in your calculator, 0.1 times 6, you would end up getting 0.60 moles of H2O as your final answer. All right, next problem. It says, estimate the mass of CO2 produced in 2006 by the combustion of 3.5 times 10 to the 15 grams of petroleum. And so our petroleum is this hydrocarbon here. So 3.5 times 10 to the 15th grams of that. And we want to know how many grams of CO2 can be made. And so if I draw my bridge, I know I got to connect these two things. Again, you don't have to draw the bridge. For me, I like the visual. It helps me focus. And I think about how many steps this should take. So if I look at what I'm starting at, I'm at 3.5 times 10 to the 15th grams of C8H18. And I want to get to grams of CO2. And so when I think logically about the steps, I'm going to first want to get to moles of the thing that I'm given. I got to first go up, get to moles first. Okay, so get to moles however we can. In this case, because it's a gram amount, I know I'm going to use the molar mass of my C8H18 to help get me to the moles of that same compound. We don't jump to CO2 just yet because we have not introduced that ratio. And so we would look up the molar mass for C8H18. And so that would be 12.01 times 8 plus 1.01 times 18. And that gives us 114.26 on the bottom is to 1 mole on the top. Now, because I've gotten to moles, I now can cross my bridge, get to here, through using the mole to mole ratio. And so on the bottom, we'd say moles of C8H18. On the top, we would say moles of CO2. And then last but not least, well, actually, before we get there, let's put in the mole ratio. So that would be 16 on the top is to 2. And then last step, now if I want to get to grams, I would put moles of CO2 on the bottom, and then the grams of CO2 on the top, bearing in mind the total, which would be 12.01 plus 16 times 2, or 32, gives us 44.01. And then when we plug this in, 44.01 to 1, when we plug this in, we would have 3.5 e to the 15th times 16 times 44.01 divided by 114.26 divided by 2, and that gets us 1.1 times 10 to the 16 grams of CO2 as our final answer. Again, just like before, get to moles first, then mole to mole, then use that gram amount, the molar mass, to get to our grams. One more example. And so this says, how many formula units of lead 2 oxide can be made from the decomposition of 100 grams of lead 4 oxide? So if we look at this, we again check it, it's balanced. I'm going to write exactly what I'm solving for right under here. So 100 grams of lead 4 oxide. And I want to know how many formula units, so I'm just going to write F units, can be made from that. And so again, let's think about the steps. We should see this can't be one step because I'm not in moles and I'm not going to moles. I know this is likely going to take 3 steps because I'm going to want to go from grams of PbO2 to moles of PbO2, first step always, then use mole to mole, cross the bridge, then go from moles to formulas using mole island or Avogadro's number. Okay, so starting with the beginning, grams of PbO2. And so on the bottom, I want to get rid of my grams of PbO2. On the top, I'm going to get to moles first. And we know we do so by using the molar mass. So for the molar mass, I'd be taking 207.2 plus 32 would get us 239.2 grams for every 1 mole. Now I'm ready to cross the bridge. On the bottom, I would put 1 mole, excuse me, not 1. I would put moles of PbO2 and on the top, I would put moles of PbO. And now when we fill this in, we look at the ratio, it's 2 to 2. And then the last step, now I want to get from moles to formula units. And remember the formula units we're using because lead 2 oxide is an ionic compound. And so we know we don't say molecules, we say formula units. So it'd be formula units of PbO compared to moles of PbO. So again, get to moles first, mole to mole ratio, then continue on. So to fill this in, I will put 6.022 times 10 to the 23rd is to 1 mole. Plug it in our calculators, and we have 100 times 2, and you can divide those 2's out if you wanted to, or cancel those 2's out. So 100 times 2 times 6.022 e to the 23 divided by 239.2. Make sure divided by 2. If you don't take the 2 off the top, make sure you leave it on the bottom. And what we end up with is 2.518 times 10 to the 23rd formula units of PbO. Okay, check your answers. Awesome. I hope this information helped you understand the foundation of stoichiometry. Be sure to like, comment, and subscribe for more content that you might want to see, and check back in for later videos where we'll be covering other topics like limiting reaction, theoretical yield, and percent yield. See you guys later. Bye.